All right, everybody, welcome to the beginning of Chapter 6. Chapter 6 is going to be all about similarity, especially with similarity relating to triangles. We'll be discussing the idea of similarity and what it is coming up later in the chapter. But just know that similarity is kind of like congruence, but not exactly. There's a little bit of a difference, and we'll be talking about that as we come up through the chapter. They're related to each other, but they are definitely not the same thing. But before we can talk about similarity, we need to talk about the idea of proportionality and proportions and ratios. So here we are at section 6.1, ready to talk about that. What a ratio is it's simply a comparison between numbers. That's all it is. If we have the ratio of A to B, we can write this in a number of ways. One way you might remember seeing is with colons, so A to B, like that. We can write it literally as A to B, as the words are. We can also have A over B as a really common way to write it. So we have a few ways to express this. Simplifying ratios, well, there are a few different approaches to take to this. When it comes to something like this first example, 12 kilometers to 3 kilometers, one pretty easy way to simplify this one would be to just divide both of those numbers by 3. And if we do that, 12 divided by 3 is 4 kilometers to every 1 kilometer. And the point of that would be, let's say that for every 1 kilometer of something happening, something else goes 4 kilometers. Well, now this is going to allow us to extend that and say, what if the first one went 8 kilometers? Ratios allow us to more easily calculate what the new value is going to be if we know one of them. The second example, 36 inches to 9 feet. You may be a little concerned that they have different units, but sometimes they will have different units, especially when it comes to things like scales. When we're trying to take something that's way smaller, like a model, and turn it into something that's bigger, like a real building or a real room or anything like that. So don't worry about the fact that they have different units, but again, we can divide both of these by a number that will make them a little easier to deal with. So we can divide both of these by 9. 36 divided by 9 is 4, so we get 4 inches for every 1 foot. That's not to say that there are 4 inches in a foot, but maybe for a scale, if we go 4 inches on the scale, we've gone 1 foot in real life, which means that the scale is about 1/3 the size of the real thing. So those are just some examples of simplifying ratios. Extended ratios are ratios that have more than just 2 numbers in them. For this example, it says a triangle's angle measures are in an extended ratio 1 to 3 to 5. Find the measures. What that means is that we have a triangle where, let's call one of the angles x. That would be our 1. If that angle size is x, then another one of the angles is 3x. That's the 1 to 3 part. And then the third angle size is 5x. Since there are 180 degrees in a triangle, we just add x plus 3x plus 5x equals 180. X plus 3x plus 5x is 9x equals 180. That gives us, when we divide by 9, that x equals 20. That means our 3 angle measures are 20, 60, and then 100. So you see that those angle measures kind of go in that ratio, which is what we were looking for. A proportion, down here, next term, is a comparison of 2 equal ratios. To solve a proportion, you're going to want to use something that you've learned in the past. Many of you learned it as cross multiplication. Some of you might have learned it as fish method. Cross multiplication is a little bit better because it works in more situations, but fish method really is just cross multiplication. So like in this first example, fish method would work, but so does cross multiplication. The idea here is that we're going to go diagonally across the equals and multiply those components. So 3 times a is 3a, and we're going to set it equal to the other one. 6 times 12 is what we had there, and 6 times 12 is 72. So we divide both sides by 3, and 72 divided by 3 is 24. So we get a equals 24. In the second example, we would do something similar. Again, cross multiplication. Look at those two, look at these two. And what we're going to end up having set up then is 2 times y plus 1. The parentheses are important because that 2 is going to have to multiply the 1 as well as the y, equals 1 times 3y, which is just 3y. Distributing this 2, we get 2y plus 2 equals 3y. And if we were to subtract 2y from both sides, we would end up with 2 equals y. So we would solve for y that way. And that's solving proportions. It's probably something that you've seen before, but we're going to need to remember about that coming up for this chapter. Ratios can also, and proportions can also allow us to check to see if two ratios are equal. Here we have 4 to 20 and 25 to 150. If we set these up in a proportion, 4 over 20 equals 25 over 150. If we cross multiply these, and the answers that we get on both sides of the equals are the same, then these ratios are equal. So we have to do 4 times 150, which is 600, equals 20 times 25, which is 500. And clearly these two numbers here are not equal. So that means that these are not equal ratios. All right, that's it for this side. Next side. All right. So one skill that you may need at some points is to be able to use some unit conversions. So what we're going to have to do then is, let's say we want to turn 78 hours into days, like it says here. So we start with 78 hours. This is dimensional analysis, like you learned in science probably at some point. So 78 hours, well, how do we turn hours into days? We need to get rid of the unit of hours. So we'll put those down here so that they cancel out. And we need to turn them into days. Well, how many hours are there in a day? Answer is 24. So there's 24. 24 hours in one day. Well, then we just sort of multiply these together. What you end up getting is 78 divided by 24 in the end. And 78 divided by 24 is 3.25. So we get 3.25 days. Notice that the hours will cancel out there, and we're left with days as the unit. So that's how that one worked. 18 yards into inches. Well, we want to get rid of yards and we want to turn them into inches. We can use 2 steps for this one. For example, we know that there are 3 feet per 1 yard. And then we know that to go from feet to inches in 1 foot, we have 12 inches. So, if you were to do all of these multiplications together, then you would have the answer as to what that was. 3 times 12 is 36. And 18 times 36 is 648. So that would give us 648 inches. Just like that. All right. So this could lead to a few other cases, like if I can run 5 miles in 42 minutes at the same rate, how long should it take to run 13 miles? Okay, so this is related to proportions. They're giving us one ratio right here. They're telling us 5 miles, 42 minutes. and we need to figure out how long it's going to take to run 13 miles. So what we want to do is we want to set up another fraction with the units in the same place. And we're told 13 miles right there, and we need to figure out how long it's going to take. So we just set up cross multiplication like that, and we are going to be good then. So we're going to need 42 times 13, which is 546, equals 5x. So then we just divide both sides by 5, and we get about 109.2 minutes. Second one here, Greg's Marble Factory produces green and gold marbles. In each bag there are 3 marbles for every 7 gold. So 3 green for 7 gold. Keep in mind that that means that when we add the green and the gold together, in this example we have 10 total. How many gold marbles will be in a bag of 50? So what we're looking for is gold marbles out of total marbles. Well, using our information from the left, we can see that there are going to be 7 gold marbles for every 10, and we're looking at a bag of 50 marbles, and we want to know the number of gold ones. So, cross multiplication will work here. If we do 7 times 50, we get 350, equals 10x. Divide both sides by 10, and you get x equals 35. So we would expect 35 out of 50 total marbles to be gold. Last idea for this part is this idea of the geometric mean. And what it allows us to do is it allows us to find rectangles with the same area. Or rather, rectangles with the same area as a given square. So, for example here, we're told that we have a rectangle that has a length of 8 inches and a width of 5 inches, and we want to know what the square's side length would be that would have the same area as this rectangle. To calculate the geometric mean of 2 numbers, in this case 8 and 5, it's a 2-step process. First step, multiply the numbers. So here we have 8 times 5, which is 40. And the second step we have is to take the square root. So we have square root of 40. We could split this one up. For 10, these are both 2's. This is 2 and 5. We have a pair of 2's, which goes on the outside. And then we have a leftover 2 and 5, which is going to turn into 10. So 2 root 10 would be the side length of that square that had the same area as that rectangle. They would both have an area of 40, but 2 root 10 is the side length of the square. Geometric mean of 1 and 9, this one's actually a little bit easier. First step is 1 times 9, gives us an area of 9. Second step, take the square root. Well, square root of 9 is 3. And that should make sense. 3 times 3 would be the area of the square, which is 9. And then 1 times 9, if those were the side lengths of a rectangle, would also equal 9. But the square has the same side lengths, rectangle doesn't necessarily. Last one here, just as one more example. 3 times 15 is 45. Square root of 45. Well, we can split this one up. 9 and 5. 9 splits to 3 and 3. We have a pair of 3's that will turn into 1 3 on the outside, and that 5 left over will give us 3 root 5. So, that's the last concept of this section. Thanks for watching the video. Next up will be a video on 6.2.